when they're not programmed. So what we have arranged is for the Dobsonian to be donated to the center, and the center will deploy the telescope to the Lennox and Islington dark sky viewing area. We retain ownership. If anything ever changes there and program ends, we take it back. In addition to the donation of the telescope, the estate has donated funding to Lennox and Addington for the construction of a shed. And for this to be a efficient operation for the people who do the presentations there, two of whom are members of our center. There's Joe Gilker and Tim Trentadew. The telescope needs to be stored in its assembled position. So this is the telescope, and this trailer is included in the donation, which is where it's stored in the off-season. So what we're going to do, the donor included funding for a storage shed and process. So this is something that is somewhat in progress, mostly arranged, and the only thing left really on the to-do list here is getting that storage shed designed and getting the telescope into the hands of Lennox and Addington. And in the spring of 26, we expect it's going to be up and running. So there's what we've been working on during the summer. Are there any questions?
Yes. I've heard there's been some issues with vandalism up there.
Yes, there has. And the designer of the shed for this is the same person that redesigned things up there to deal with the past vandalism. He designed it initially and then made adjustments. And so it is something that they have taken into consideration and are taking into consideration.
I have another question.
Yep.
So, work mate of mine, her husband died, but he had telescope so I haven't been over to look at it yet, but do you have any need of another scope?
Right now, we're kind of limited in the space we have for storing them.
Yeah, the question is, where would it be stored? If you can store it, then we can take it.
So would we be able to put a black scope in the same?
What kind of scope and what size?
I believe it's a 6-inch.
Is it like a refractor or a reflector? Would you be bringing it with you, I suppose, then in the future for use on certain nights?
It's hard to say because we've got 2 scopes already. We can bring our own scopes. Find our own. It's hard to say.
Okay, well, let's take it offline and see if we can find a way to make it work.
I just, when this is ready to have first light at Lennox and Addington, I think it would be really nice if as many of us got there as possible.
Yeah.
Just,
yeah.
So let the date be known as soon as we get an idea.
Yeah, for sure. And Ingrid too, yeah.
You're gonna put like a date on it or something, or
It already has it.
It's on it, and
Yeah.
it's going to be involved in the Kingston Centre or something like that.
No, I think that's extreme. But the base has, you can't see it in the photo, but there is a plaque there that a session actually made that's for the purchaser, and it's got Attila's name on it. So.
And what number of
Okay. Anyone else? No. The monthly newsletter Regulus is out from Roger Hill, and there's actually a piece on that telescope in my report for September, along with lots of other
interesting reports from other members, and it's available on our website at kingston.rasc.ca. Out of order. Sorry, Rick. John Hurley.
Hello, everyone. This past Sunday, National Council had a meeting, and there were a few issues brought up. One was some national offices starting to hold some training sessions. One will be for the treasurer positions across the society. So any member of the society can register for that training course. If you're interested in becoming a treasurer at some point, not necessarily even this year, but you're just interested in the process, you can certainly attend this session. And the keep track of the national website. There are other training sessions being offered, such as Stellarium, the planetarium program that just did some. We got one started off for Stellarium on your mobile device. And they also have a series running on desktop. Our national president, we changed this summer, and is now Brendan Roy. He's been on the board for a number of years. And Michael Watson, our previous president, has now taken over the position as treasurer. And the national spending has been under a microscope now for a couple of years or so. They've got it down as much as they think reasonably can control, but they're still short on revenue. So if anybody's got any ideas on how to generate revenue for the society, please share. Yes. And in the meantime, if anybody has any interest in any of the RASC merchandise that's on the website, please check. There is an assortment of interesting RASC labeled apparel, from toques, jackets, warming things for keeping your neck warm. There's a slew of books and publications that are available. Makes wonderful presents for the budding young astronomer in your life. That's nieces, nephews, grandchildren. There's a lot of things there. Coffee cups, that will also help the revenue side of the society. At the moment, the membership fees are coming due for most of us, and there's no change from last year. And everything's done online now. There is no grace period. In previous years, your membership expired, and you had, I think it was 30 or 60 days after to renew, and then everything was all seamless. But that was turning into a bit of a nightmare for the national office staff. So now they've changed things, and everybody can renew up to 90 days before your renewal date. Do that online. You'll be receiving some emails on reminders at 90, 60, and I think 30, but I'm not sure of that. If anybody's got any problems with the new system, please let us know, and we'll help guide you through it, or we'll find out what the problem is, and National will get over it, get onto it. Our executive director, Jenna Hines, is already looking for topics for next year's General Assembly. So if there's anything you'd like to see here, let her know and see what we can do about getting that onto the agenda for the GA next summer. She's going on an extended vacation at the end of September, so if you're going to get in touch with her for any of this, please do so soon. Otherwise, wait till the latter part of October. This is going to be the longest vacation she's ever taken since she started working, and she's really looking forward to it. The website for the National Society is being upgraded. So at some point in the next few months, there will be issues on certain days as they do the changeover, and hopefully that goes smoothly. They're trying to, right now there's two websites. We have the web page with, what's up at the society, and then you have the members login portal. That's all going to be combined into one site. So it should be a little more seamless for our members and the public. There'll be the part that's open to the public and the part that we log into. And so that should be interesting. They had hoped the changeover would be relatively simple, but the website was written in some very old code that is not compatible with the newer stuff. So basically, they're going to redo it from scratch. That's what I believe is going on there. So that's taking longer than they had hoped, but it's coming. National Office is also looking for anybody with French skills. They want to bring the green laser pointer program into English and French versions. So if there's anybody with any experience of that, they're looking for some help with preparing the material and offering the course in French to the French-speaking members of the society. And as many of you know, we've been having issues with our neighbors to the south. And a lot of the revenue that National Office generates is from sales to American customers. We sell a lot of handbooks to the American down south and at a very good markup. So that helps our finances. And we sell a lot of other paraphernalia that way. And fortunately, the changes to the programs of sending stuff into the States means now for each and every order into the state, National Office has to prepare a form for customs to accompany that order, basically to say that there will be, and since everything we have is publications or is under the free trade agreement, and so pretty much nothing is subject to tariffs, but you still got to prepare this form and send it with the shipment. So that means more staff hours are being spent on this sort of stuff. So we'll have to keep track of how that works and they have to adjust shipping and handling charges and stuff like that. But so far, not as bad as it could be, which is good news. Oh yeah, and as many of you know, at the annual meeting there earlier this summer, we changed our auditors, and National Office is changing how they do their audits. Part of the deal was, and this was reducing the cost of the society, is we're going to do national books will be audited twice a year, in the fall and in the spring.
In the fall, reflecting the
year-end.
spring, and then
Yeah.
at the end of the
So
year.
it's the other way around.
Yeah.
They're doing the year end now, big stuff,
Yeah.
sort of. But so this should make keeping track of the financial matters at the National Office a bit simpler. They've been, National does everything by a month, and that's been reviewed every month for the last few years. And so far, it's been going fairly well. The deficit has been dropping. We probably aren't going to quite balance this year, but our revenue is down this year over what was projected. And some of that is simply because we don't have a big item going on in the sky right now. Like in a year where you have a solar eclipse happening, membership numbers climb. In a year that's more normal, our membership drops down a bit. If we have another big astronomical event, our numbers might go up a bit more. So various membership numbers are down a bit this year, and of course that means a lot of other things are down. And some of the expenses are down, but we're not going to quite balance the books, looks like, but it should be within a few percentage, so that's pretty good. And the other big news is for any of the longtime members, the Windsor Centre, which I happen to used to be a member of when I met my wife-to-be Peggy at the time, is holding their 80th anniversary this fall. As being part of the society, and they're having David Levy as their guest speaker. So if anybody's in the interest in the Windsor area on November 15th, you might want to stop in.
Why not?
Yeah, we're going to be there, and I hear a bunch of people from London are coming down, and some past presidents of the society and a few others are going to try to make the attempt. it should be fun. I was there at Windsor's 40th anniversary, so kind of fun to make the 80th. And there's still a few familiar faces kicking around there, so it'll be interesting. And if anybody else wants to come, please let me know and I'll give you some details. Thank you. Is there any questions, concerns of the society? Okay.
Oh, no.
Yeah. Be polite, Kevin. Thank you.
Okay, and now there's a 5-minute break. No, just kidding. Rick Wagner is going to present on photometry. Let it open. So that makes it slideshow on the screen.
We don't have much storage space here now, right?
There's room for the fixture. And it's really great.
Well, good evening, everybody.
That's what I thought.
Some of you will probably have noticed over the years that I do have a big interest in photometry. And I often talk about what I've been doing and some of the results and stuff. I thought it's about time I actually told you what I'm doing when I do photometry. So get ready, you're drinking at the fire. And now half of my slides not showing up. Anyway, so why do we want to do photometry? We want to measure the light, the intensity of the light coming from various objects in the sky. My main interest is variable stars. These are very important. A lot of them pulsate, and the pulsations are driven and controlled by the interior structure of the star. So by looking at the pulsations and how they change over time, we can get information on the structure inside the star. They're also important for the evolution of stars by looking at different stars in different phases of their life and stuff. We can learn about their evolution. Because we can measure the distance to stars, particularly pulsating stars, by knowing their period and so forth, we can get information on galactic structure. And eventually, if you go look out far enough to the Cepheids and then into supernovae, you can actually get information on the scale and the evolution of the universe. I've done some asteroids. You can measure their rotation periods by measuring their, because they're usually sort of potato shaped, a lot of them. If you measure their light curve over a period of time, you can actually determine their shape. Exoplanets is the big thing right now, and timing of an exoplanet as it goes in front of its star is very interesting. There's way too many variable stars. The AAVSO has their international database of variable stars, currently sitting at about 10.8 million. There's lots to look at, not very many telescopes. A lot of the targets the professionals can't handle, mainly because they don't have as many telescopes either, but also a lot of stars are too bright for them. They vary over too long a period. They can't get allocation of time on the telescopes and so forth. And finally, a lot of the professionals just aren't very good at it. So we start off back at basics. The magnitude of a star is how we measure its brightness. It originally started off with Hipparchus. This is his imagined appearance by Raphael. And basically, it wasn't a numerical thing. There was different classes of stars. So a really bright star was a star of the first magnitude, and so forth, down to the dimmest stars you can see were stars of the sixth magnitude. Similar to the idea of Meryl Streep as an actress of the first magnitude, Adam Sandler as a dim bulb who shouldn't even be on. Okay. So measuring the brightness of stars was introduced in the 1800s. Friedrich Argelander was one of the very first, and what's really neat is he actually requested amateurs to give estimates of variable stars. So it started way back. And the AAVSO was founded in 1911, primarily to collect this data and encourage variable star observations by amateurs. So it's all done by the human eye and using comparison stars. So we're comparing our target against stars of known brightness in the field. It's differential. We're always measuring how bright is my target star compared to some other star in the field. Not very accurate. If you get really good, you can get down to about a tenth of the magnitude. Most people are around a quarter. And surprisingly, the human eye is pretty good, about 10% quantum efficiency. Under ideal conditions, you can actually occasionally detect individual photons with your eye. So how do we do this? We go to the AAVSO or the Germans or the Japanese or the British, and we get a chart. So here's a chart right around here. There's our target star in the center, and then the stars of known brightness are all marked. They leave the decimal points out so you don't think there's extra stars in there. And basically, we're going to compare our target star. So I've reoriented the chart slightly so that it matches the scale with this. This is a little crop circular, so it looks like a telescope view. This lovely picture by Malcolm of T-Corbor. So if we go back and forth, you can see. So here's our target star, T-Corbor. This is the 9.8, 9.3, 10.6, 10.8, 10.7. So basically what we do is we look at the star, we decide, well, it's fainter than the 9.3, but brighter than the 9.8. So it's somewhere in there. And so imagine, think of putting these two magnitudes on a line. In this case, because there's 5/10 of a magnitude, you might imagine splitting that line up into 5 pieces and saying, well, the star is, say, 40% of the way from the 9.8 to the 9.3. So we'll call it a 9.6. And that's what you would report to the AAVSO. So they did start developing visual photometers. They used like graduated wedges and stuff and comparison bulbs and stuff to try and get better precision. And they did get down to about a tenth of the magnitude. One of the big issues, no permanent record. You mess up, you pick the wrong comparison star, the wrong target star. An hour later, it's toast. That's just a ruined observation. So then we moved into photographic. They started using glass plates. Almost as soon as photography was invented, they started doing astrophotography. It does have a permanent record. You can go back and look at that plate for centuries, decades anyway. Problem is, they have a nonlinear response to light, very low sensitivity, about 1% quantum efficiency, limited dynamic range. You can only really use them over a couple of magnitude range. They were used up into about the sort of the 1950s, 60s. And one of the best examples is the digital access to a sky century at Harvard, which is where they digitized 550,000 glass plates stored at Harvard College Observatory. Those are all now available online. You can look them up and you can get copies of them. So here's an example of one. The astute among you will immediately recognize the Lagoon Nebula, the triplet M24, and down into the Milky Way. So this, I'm just guessing from the scale and everything, this was probably taken with the 10-inch Bruce camera. This is a particularly exciting image for me. I actually, when I was down at Harvard College Observatory, I actually got to see the physical plate. And this is the Andromeda Galaxy, and Edwin Hubble is marking out novae that he's discovered in the Andromeda Galaxy, including this nova, which he then went, oh, that's not a nova. That's a variable star. That was the first extragalactic Cepheid ever discovered, and its period and brightness was essentially locked in the fact that this is an external galaxy. It is not a spiral nebula in our galaxy. I've subsequently done maybe 30 or so measurements of that star. So then we got into photoelectric photometry. Was popular in the late 20th century, uses photomultiplier tubes. Some were doing photodiodes, but they're not very sensitive, so they don't work very well for anything other than white stars. The 1P21 was the photomultiplier tube of choice. This is what it looks like end on. Photon comes in here. It's this, kicks off an electron, which goes over here. It's sped up by the electric fields, smacks into here, pumps off 10 electrons, which becomes 100, 1,000, 10,000, 100,000, a million, and so forth. And eventually it comes here and it gets collected. And so with a steady stream of photons, you get a continual, very, very small current out the bottom of the tube. Or if you're good and you have good equipment, you can actually count the individual photons, little pulses of electricity come out. So this is a modern day photometer. This is the Optec SSP5. Your light comes in from the telescope and comes to focus on a little metal disc here. We have to separate the star out from all the rest of the light. So we have a little hole here. You can see 1 millimeter standard on an 8-inch f10 scope. That's about 100 arc seconds across. The light gets focused by a Fabry lens into the tube here onto the photosensitive area of the photomultiplier tube. I don't know what these things cost. I don't think they make them anymore. So if you want one, you have to find them in the used market. High precision, better than 100th of magnitude if you're good. On the other hand, 1 star at a time, if you want to measure something. So here's our field, T-core bore. We take our telescope, we center it very precisely. Oh, first, we select our V filter, center the telescope very accurately on our star. We take a reading for 10 seconds, write that down in your notebook. Now, clearly, there isn't just starlight coming in that little aperture, there's also skylight. So we move over to a nearby empty patch of sky. Hopefully, no little stars in there that we can't see in the eyepiece. Take another reading for 10 seconds, write it in the notebook. Go off to our comparison star, do it again. Go off to a check star, do it again. Go to our B filter, do the whole thing all over again. Then do all of that all over again 3, maybe 5 times. So you've got some statistical sampling and you can actually come up with a reasonably good magnitude and estimate of your errors. So you can see, again, no record. You mess up, you pick the wrong star, you don't get the star centered and part of its light is cut off, anything like that. It's a useless observation. You've lost that observation and an hour of your time. So the other side of it, though, is it can be very high speed because this thing can actually get down to where it's actually counting individual photons. You can do really cool things like, have you ever watched a star being occulted by the moon? Disappears instantaneously. Well, not if you have a photomultiplier photometer. You can actually watch the diffraction pattern as the star disappears over 100th of a second. But no permanent record. So finally, we get into the array sensors. In other words, a block of pixels, CCD and CMOS cameras. CCDs are disappearing. It's certainly from the amateur world. But CMOS is almost all you can get now. Digital sensors, very high quantum efficiency, like up to 90% or even better. Very linear response. You can measure stars over 5 magnitudes or 6 magnitudes on a single image. Wide dynamic range. Simultaneous measurement of many stars. I can take one image and come up with 1,000, 2,000, 3,000 measurements of star brightness off of one image. With practice, you can get down to better than 100th of a magnitude. And you've got a permanent record. Anytime you decide you've messed up or you want to reanalyze something, you can just go back and look at your images again. So what are we going to do? We can do all sky photometry, which is basically, this is how you would set up comparison stars, for instance, or to make secondary standards. You would image a standard field in one part of the sky, and then you would go over and measure another area, and then you correlate between the two. Very difficult because the extinction of the atmosphere might be different than it is here or there, or with time, 10 minutes between these observations, air glow, clouds, all kinds of things. Very difficult to do and requires a great deal of observations. So what we do instead is we use differential photometry. We take an image, we use comparison stars that are in the image. That means there's no variation in atmospheric extinction and so forth. The stars are all close to each other and they're all taken at the same time. We're measuring the relative brightness, differential. So we have a comparison star. What's the difference in magnitude between the variable star and the comparison? The check star, we'll get to the check star later. Difference between the check and the comparison. So no or almost no atmospheric and instrumental effects. Once we've decided this is what we're doing, we can do 3 primary different types of photometry. We're going to discuss aperture photometry. That's what almost all amateurs use. It basically gets back to the idea of having a little disc, right? With our photoelectric photometer, we had a little hole to let the starlight through. We're going to do something similar here. So what do we do with each image? You apply bias dark and flat. Very critical if you want to get accuracy, and that's all you do to your image. You don't mess with it. Select your comparison stars. You set these little apertures around the stars. Measure the amount of starlight in each aperture. Calculate and do a light. So clearly, if we're going to get hundredths of a magnitude accuracy, we can't depend on a chart that has magnitudes only to 1/10 of a magnitude. So we go back to the AVSO and we get the photometry, detailed photometry. Magnitudes are all given to 1,000th of a magnitude. Generally, the accuracies are a few hundredths of a magnitude. So here we have our field. This is one of my images, and you can see it's scaled up. So this is the target, and I think these were the 2 nearest stars. So what we've done here, let me zoom in a little bit. So I've made my little aperture around the star. And you can see that this aperture here is probably 8 arc seconds, maybe 10 arc seconds across, instead of 100 arc seconds with the photoelectric photometer. But again, there's going to be skylight. coming in through that aperture in addition to our starlight. So we make a ring, an annulus, around the star where we measure the brightness of the sky background. And what's nice about this is, for instance, if there's a gradient across here, it's averaged out by the fact that we're measuring all the way around the star instead of just off to one side. And you can see the speckling in here is the computer has actually looked at all the pixels in there and decided that all those white ones are sufficiently weird, statistically speaking, that we're just going to ignore those. And we'll only use the black pixels. So for instance, if there was a faint star in here, even several, it will ignore the star and give us a true reading of the background. So we put a similar aperture and annulus around our comparison star, and we do it around our check star. Now, let's talk about check stars. Why do we need a check star? Imagine if you're a carpenter measuring the length of a bunch of boards. You're down at one end with the tape measure taking the readings, and your assistant is down at the other end. Oh, and he's just sort of putting the end of the tape somewhere wherever he feels like it. And you get down at the other end, and your 8-foot boards are all 7 foot, 8.5. Like, what the hell's going on? If this star, we're measuring our target against this comparison star. If this comparison star varies, our 0 point is moving while we're trying to measure the target. So what we do is we have a check star as well. We measure its brightness in comparison to the comp star. If this one appears to vary, either it could be this one varying or it could be this one varying. But in either case, we know we've got an issue. Now we have our permanent record. Yes?
Just at this point, you're doing this digitally after the fact. You've
This is
taken
all
the one.
after the fact.
Okay.
This is based on just on the image.
These are not 3 different images.
No, this is all a single image.
Just wanted to make sure I knew that.
Yeah. So if this star seems to vary, it could be it varying, or it could be our comparison star varying. So now we have the permanent record. I can go back to the image and say, let's use this star as a comparison star and a check star. And then we can figure out which of these two is varying, and we can correct the situation. The other nice thing about this, as it relates to Susan's question, is I've got 1,800 images like this. I go blink, think, think. Once I tell my program, save these positions, you can see here, when I click on the stars, I tell it that this is a 9.809 magnitude star. Instantly, it tells me that this one is 9.963 and this one's 11.055. No calculations, no thought necessary. And because I can then tell the computer to save these positions and magnitudes, I can say, okay, now do the other 1,000, 2,000 images, and in about 30 seconds, I've got all the data I need. Yes, Lord.
So what might cause the stars to vary?
Well, there's lots of variable stars. So for instance, if we didn't know that this is actually a pulsating variable or an eclipsing binary, you know, it might be just a little fainter one night than normal. Well, for instance, an eclipsing binary, it goes along the same magnitude and then drops for a day or two. So all of a sudden our 0 point is not where we thought it was.
So you don't necessarily priority know that the stars that you're using are.
No, in fact, as far as you know, you pick them because they aren't variable. But a lot of times, like you look in the amateur papers, the information bulletin on variable stars and stuff, there's often papers, 4 new variable stars discovered in such a, and it's people who have done this and something's wrong between these 2 stars, and they research it and they discover that's a variable star. They report it, they figure out what its type is, its period, and so forth. So, once we got a whole bunch of magnitudes, we want to look at a light curve. The magnitude is a function of time. We always show the variable star and the comparison star, and we try and highlight the variability that we're looking at go. Oh, there we go. All right, this is my favorite light curve that I've ever produced. SZ Lincus is a high amplitude delta shooting star, about a half a meg.
No, it's back, it's back.
Oh, okay. About a half a magnitude variation. I think it's about 2.5 hour period. So what I've done here is you can see I've observed it from February 2015 to November 2016. And what I do is, because the light curve is basically the same every period, I can take them and fold them all together and overlap them all. And they all overlap very nicely. Although you notice there is some scatter here that one would try to avoid. But in fact, in this case, what it is this is actually called, well, the light time effect. The pulsating star is going around another star. So when it's close to us, the maximum light happens 5 minutes early because it's closer. So it doesn't have, the light doesn't have as far to travel. When the star is on the far side, the light has to travel the extra distance. So all the brightnesses are all 5 minutes late. So by doing this, if you do this for a few years, you can actually determine that this star is actually going around its companion in about 1,800 days.
Question.
Yeah.
So you always corrected for the orbit of the Earth around the sun?
That's, yes. Yeah, we do the things, it's called heliocentric Julian date. So yeah, when we're on, because it's about 8 minutes each side. So you always correct for that. And then this is the variation of the comparison star. You can see this is 200ths of a magnitude. So more scatter than I would like, but this star is magnitude and a half fainter than the target. Yeah, Mike.
So Rick, nowadays with like the normal CCD camera, it just use a program to see the people.
Yeah, it's not ideal because the color filters in it are not standard photometric filters, but a lot of people are doing it, and with one-shot color cameras and stuff. So details. I think that's what I'm talking about. Sampling. When you have a CCD camera, particularly the CCD cameras, the older ones are front illuminated. There's a lot of electronics that runs along in front of the pixels. So in those areas, the pixels aren't sensitive to light. So if you have a really nice telescope and good seeing, and your stars are very small and your pixels are too large, this one we catch all the light of this star. Here we're missing almost half, and here we're probably missing 3/4. So this star is going to look anomalously faint compared to this one. So we always want to make sure we make our stars big enough that they cover sort of that one size. You get too big, and you start getting too much sky noise in there, and it affects your observations. Nonlinearity and saturation. The cameras are very linear. This is a measurement. This is the one that used to be the 16803 that was on the RASC remote telescope. And you can see that's a pretty nice straight line. And it reaches right up here to about 65,000, which, if you know, to the 16th, it's a 16-bit camera. It can't put out anything more than 65,000. So that's when it goes nonlinear. But even up here, you can actually see, if you look carefully, it's beginning to droop off a little bit. So I probably wouldn't use this camera beyond about 60,000. Other problems, atmospheric transmission. Not only does the atmosphere block the light, but it blocks the blue light worse. So it changes the colors of the stars. Scintillation, what we know is twinkling. Basically, if you take short exposures, some exposures will catch more light, and some will catch less. So unless you're basically you want to keep your exposures sort of 10 seconds or longer, or add a whole bunch of them together if it's a bright star. Sensor response, this gets back to Mike's question. The sensors, all the cameras are different, even the same model, there's slight variations, and the filters are different. So they let through different regions of the spectrum, and that will affect the quality of your measurements. Clouds go by. Most of the time, if you're shooting with a telescope, it's not a problem too much because the field is relatively small. So broad, thin clouds don't have a great deal of effect, but if you're going wide field or if it's sharp-edged clouds, it can affect. You put that little aperture around the star. You want to make sure you get the right size. You want to make sure you calibrate your images, your bias darks and flats, do that properly. And of course, you're always subject to cosmic rays and hot pixels that will just spontaneously put bad information. Difficulties, bright stars. Your camera will saturate in a long exposure. So you need to, like for instance, I'm observing X Cygni, which is around 6th magnitude in visual. And I'm doing 1 second exposures. So I do 20 of them and average them all together. If you get close companions, you know, if it's always inside the aperture, you can correct for it. If it's outside the aperture, you don't have to correct for it. If it's part ways inside the aperture, then depending on the seeing, depending on the aperture, sometimes it's present, sometimes it's not. You get a lot of scatter. Meridian flips are a problem if you're trying to do really high precision photometry. You flip your telescope over a German equatorial. All of a sudden now your camera's upside down, your stars are all in different places. If your flats and so forth aren't really good, you'll notice, and I've done this with exoplanet transit, you get your star and it's going along nice and smooth, you do a meridian flip and suddenly it's up there. It's like, eh. The only nice thing about that is that it says, hey dummy, your flats are bad, you need to go back and fix them. So there's a lot of software to do this. The aperture photometry tool is really cool if you want to look at a single image or 2 images and really burrow in and figure out about like the shape of your stars and all kinds of interesting detail. Astro Image J is really nice. That's the one I was showing earlier, and it has all kinds of tools. It's intended for exoplanet transits, so it's got all kinds of extra tools for that, but it does great photometry. It's really easy to use. It's really fast. Lesba Photometry is a guy in Belgium, Pierre Pompier, who wrote that. It also is very good. AIP for Wind, that's the software that was associated with the atmospheric image or astronomical image processing for Windows book. Commercial package Forenso. I haven't used it yet, but I've read about it and it looks really neat. It does things like finding all your comp stars automatically and all kinds of cool stuff. Not very expensive. Maxim DL is very expensive by amateur standards, but is quite capable. And of course, you can do like me and roll your own with all the AstroPi libraries. It's really and that's all I have. Unless anybody has questions. Yes, Lori.
So what percentage of stars are not binaries or higher order?
I think they say that about half of stars are members of the binary.
So
Now, most of them aren't eclipsing, so they don't vary because of that.
but I guess most of those would be too close to ever resolve.
Yes.
So is there a chance that you're looking at something thinking it's a variable, it's actually 2 stars and you're confused?
I mean, the eclipsing binaries are 2 stars where they're going around each other and one goes in front of the other. And so, of course, it's blocking the light of the back one. And those are very interesting. A lot of people like to observe them. a lot of times you get mass transfer between stars, like stellar wind or a stream of mass from one to the other, so the period changes. If they're elliptical, you can actually, sometimes, a lot of them, the bright star gets occulted by the fainter star, right? So you get a big dip in brightness. But then when the bright star goes in front of the fainter one, you'll get a little dip. Well, if it's a circular orbit, you'll always have them half a period apart. But if it's an elliptical orbit, you may find that you get the primary and then the secondary, and then a primary and then a secondary. And you can actually watch over a period of years, you can actually watch that secondary move, the secondary eclipse move as the orbit precesses. And then, there's changes in period, there's changes in color. If the two stars aren't the same color, you'll see, it'll drop more in the blue than in the red, for instance. So that can tell you a lot about the color, the temperatures of the stars, composition. Some of them stay constant. They do an eclipse and then they stay constant. Others have a sort of a gentle curve and then do an eclipse and then a gentle curve. And that can be because of, for instance, if the stars are close enough together, they actually become egg-shaped. And you get what's called reflection effects, where the hot star is actually heating up one face of the dimmer star. And so then you'll be able to measure that. So there's all kinds of interesting astrophysics you can get out.
I have a couple of questions. This does raise another one. So you're talking about eclipsing brightness.
Yeah.
I get that. But if I've got a separate variable, the period luminosity relationship,
Yes.
something, if it's part of a binary, doesn't that screw up your period luminosity relationship?
Yeah.
So,
So what you do is when you're analyzing stuff and you plot magnitude and period and magnitude, and you go, there's some, there's like 4 of your Cepheids aren't in the right place. They're all
only
too
if you know
bright.
the distance. Only if you know the distance.
Well, that's part of the calibration process. For instance, you would look at the Large Magellanic Cloud. So essentially, they're all at the same distance.
Do we see those sorts of anomalies?
Oh yeah, yeah, yeah. So essentially, if you imagine that if there was an equally bright star in a binary with a Cepheid, and the Cepheids don't seem to, the pulsating stars don't seem to have very many companions. I'm not sure why.
But it'd be too bright for it.
It would be too bright for its period, and so then you would just reject that one.
In your sample photograph, you're looking at the target star, your check star, your calibration star. I'm a little disturbed that you had like several hundred stars in that, and you're only using 3 to make a measurement. Why the whole deal?
Well, partly because in a lot of cases, you saw the chart I used, there was only maybe half a dozen stars in the field that had been measured accurately enough that you would want to use them.
That's still the case with, water databases and high emissions.
Well, that's when you start getting, it's called ensemble photometry. And then, for instance, with the new APAS, AVSO photometric all sky survey, they've measured this brightness of all the stars in the sky, sort of between about 7th magnitude and 16th magnitude. Not very accurately yet. They're still trying to do the statistics. This is this all sky photometry, right? You're trying to compare this star against that star.
So short answer is we're not there yet.
No, we are. Yeah, we absolutely are. And I do that for some of mine. Generally, I don't use all the stars in the field. I will pick maybe 10, 20. Ideally, you should have stars that match the color of your target, because as I said, the atmosphere blocks blue light more than red light. So if you're looking closer to the horizon, say, you know, your blue stars are all gonna be a little bit fainter than they should relative to the red spectrum. So when I do it, when I build an ensemble, I go and I get all the magnitudes, maybe 2,000 magnitudes of all the stars in the field. Then I filter that these ones are all too bright, so they're saturated. These ones are all too dim, they're low signal to noise. These ones are the wrong color. So then I end up with 6, 8, 10.
So how much, when people like you are doing is contributing to new science? Again, competing with, you made the comment earlier, there's lots of amateurs, not much professional class, so they're doing this kind of stuff. But there's also automated systems and spacecraft and.
Yeah, but they don't, mostly they don't cover the whole sky. They don't cover it all the time. And now certainly recently it is getting more difficult. Things like the transiting exoplanet survey satellite is measuring big swaths of the sky for a month, but then it doesn't come back for 13 months. So, you know, there could be things happening during that 13 months. They also have a very big pixel size. So there might be 4 or 5 stars in their pixel. So they say, you know, this star is doing something. Then the amateurs come along with a higher resolution telescope and say, well, you know, 3 of the stars are constant. This is your target star, but beside it is an eclipsing binary that's actually screwing your whole pixel. So none of it is something you want to be interested in as an exoplanet.
And those are things that amateurs are.
Absolutely. Yeah. Every Sunday, I get a report from the AAVSO saying how many of my observations have been downloaded. And I'm usually around between 5,000 and 10,000. So that's time to go and look for more. Great.
Yeah, I was just wondering, tonight, but began using TCPR.
Yeah.
And I was just wondering, what
yeah, I don't know that there's a great deal that we learn from our observations. You know, I'm observing it in blue and green light. So I am, you know, giving more information, say, on the temperature of the star. You know, it's just useful to know that it's you know, it got bright for a little while, you know, like a magnitude brighter, and now seems to be tailing off, and then it got a little brighter, and you know, so it just helps us understand maybe where the star's operating, kind of. Is it going to blow up soon or not?
Yeah.
And just the fact that I can go out tonight and say, well, it's 9.8 magnitude. It's not at second magnitude. You know, if I go out at second magnitude, the whole world erupts. You know, everybody's taking pictures of it. All the professionals, the satellites and stuff. Everybody's going to be on it, unless I get it wrong, which somebody did last week. Send out an email saying, I think it's gotten bright. A whole bunch of people got into a panic. So somebody else got to measure it.
So basically it hasn't changed.
No, a magnitude or so.
Yeah.
Which is what led us to believe that it was about to erupt.
Yeah.
Because 80 years ago, it dropped down for about a year and then exploded. So ours dropped down. So after a year, nothing. So.
But over the, so one last question, just over the many years, how many times has this happened?
I think this will be the 3rd that we've sort of confidently and accurately, reasonably accurately measured. So there was one 80 years ago, one 160 years ago. Then there's another one, possibly another 100 or 200 years before that. And then there's suggestions that there was one, I think, back in the 1200s, but it's getting pretty tenuous. Records were no permanent record.
Thanks.
Susan.
When you take your pictures and you're analyzing stuff, is there a limit to how close you go to the edge of the photo for your comparison?
Usually, yeah, but it doesn't, it's not a big problem. I usually keep like 10 pixels inside at least. I prefer to keep closer, the closer to the middle, the better.
When you talked about sampling and the size of the star versus how many sensors pixels you're hitting, and you said make your stars bigger. Is this like just a focusing issue, or what is it?
Yeah, I mean, normally what you would do is you would try and buy a camera that suits your telescope. But if the pixels that you've got are too small, then you can defocus the telescope a little bit. If your pixels are too big, if your pixels are too big,
you
defocus. If your pixels are too small, you can bin them 2 by 2 to make your pixels all twice as big.
Okay. And the other thing is this Ferrazzo.
Yeah.
Does it supply? Is it wonderful because it supplies more comps?
Well, just because it's well written and it's the software is good, the procedures are good, but also it does so much of the work for you. It takes me several hours to come up with comparison stars for a new variable, and mostly I like to observe stars that nobody else has observed.
Yeah.
You know, I mean, you go and do an observation of Tycho Bor, and oh, good, now there's 143,901 observations in the database.
When you look for your mark, you can't even see it in the graph anymore because it's I don't record that. I look at it, but I don't record anything. Okay, thanks.
Okay.
Mike, just quickly tell us what the ESO, did they just make a database of the stars and the observations, or did they do any crunching of that stuff to see if there is a mix of that?
No, they're just databasing and training and so forth, so that people can do a better job. But primarily, they're a repository that professionals can go to and download data.
Yeah, I was just wondering about the specific filters that you use for photography. There, I assume they're different than you like use for RASC photography.
Yes. Yeah, and they're just different. The main thing is that they were originally developed by a guy named Johnson back in the 1950s or something, using photoelectric photometry. And so he picked green glass that very roughly matched the response of the human eye. So and he called it a visual filter. So the idea was that he can do a photoelectric measurement with his V filter, and it should come up pretty close to what we would see a star. And then, then they picked some blue glass and so forth, and gradually expanded it out. But the trouble is they're all different. So what you end up having to do is you take a picture of a standard field where Arlo Landau generally is the guy who did it all. He's measured these stars, the brightness is down to like 2,000ths of a magnitude. Dozens and dozens of images over dozens of nights. And basically I can see, for instance, on blue stars, my magnitudes are all a little too faint. On red stars, they're all a little too bright. So I end up with coefficients that I can apply to my data that correct my sensor and my filters back to more closely match what he would have.
That's kind of a calibration process you go through.
Yeah.
So, with variable stars, let's say you've got variable star all on its own little binary. If you actually do spectroscopy, are there any changes in the spectrum of the star as
It depends on the star, but yeah, an awful lot of them, yes. For instance, the temperature, I mean, just a simple RR Lyrae star, or that adds the SZ Linkus, it will actually be hotter, brighter, cooler, so its spectrum will actually tilt slightly. Some of them, you'll notice that the brightness comes down and then has a little hump, and then goes back up, down, does a little hump. That little hump is actually shock wave generated inside the star. And so, for instance, in a lot of cases, you'll find hydrogen and maybe helium emission lines will suddenly show up during that little hump. So that just gives you further information on what the stars do.
Thanks, Rick.
Okay.
Take a 5-minute break.
I'll sit down and shut up for 5 minutes.
That was a lot of information.
Yeah.
More than
Yeah.
one, very first slide.
Well, if you have any more questions.
It continues during the break.
Yeah.
There's nothing wrong with working.
That's right. Lights.
Turn the lights on, it's going
Yeah.
on.
Yeah.
Turn the lights on, it's going on.
Got it.
You can actually.
Oh.
Oh, yeah.
We can put it up.
Yeah, so. Yeah.
Mark, would you like to go first?
It's all calibrated, like you got calibration stuff, it's just. It's hard to say.
That's why I talked years ago. Talking about,
Well, I don't know.
binary
Remote telescope service.
here's a binary.
Because I noticed what's there is. You might only get. Like in this. No, rather.
But don't worry, I'll calibrate this stuff.
Yeah. I downloaded. So it's not impossible, but it's quick. Okay, I'm gonna pick the one that
New stuff, you say this one.
It's interesting that.
Between the lines, you're not sensible. Down between the lines, it always comes in line. Here I am.
Yeah.
Satellite tracking.
Yeah.
You a single photon and it operates, they operate all the time. Single photon. They only want to get one photon back. Now, a whole bunch of photons back. So they sit on this. You see, well, it's just, the fact that it's individual photos.
And they have a laser, they do laser lenses, which, this comes up with selfie.
Whatever you say,
Could be, but you have a laser post. You're not allowed to use it if it's more than 5 millimeters. They're using 50 gigabytes.
Yeah.
But they get nuts because they close it.
And there was an explosion in the blood, and this insect remained. This insect is but they do such things. There's this little rubber band. Laser ranging search. They're usually they know they can measure what time that but they're all crossed out. They measure time differences. Actually, they go ahead and measure. You're on it.
Susan, are you ready? Is it
For
still,
what?
is it still recording?
Oh, yeah.
Okay.
Yeah, I never stopped it
All right,
because I
great.
was busy.
So Rick, welcome back.
Yay!
Drag it off into the other screens. The arrows will advance your slide.
All right, back to part 2. The Rick Wagner Pony Show. So, astronomy this month, September, local events. I discovered where the Queen's, or the Queen's Astronomical Research Group, that's what it is, where they hide all their seminars. So, lots of seminars, dwarf galaxies, dark matter and cosmology, star formation, and galaxies over the next month or so. Also on the 13th of Saturday, Queen's Open House. This is the subject of the Open House. Bubbles of light. This is all those caves, kind of the cavern things we see in our nebulae. No BAA events that are broadcast. No AVSO. Lennox and Addington, Saturday night triple feature, so that's the moon, the 16-inch telescope, and a laser guided star tour. The 20th following weekend, their astrophotography session, and the weekend after that, a laser guided star tour. North Frontenac, they're having the Festival of Stars at the same time that we're all going to be at Stars. That's good. Anyway, we're coming up to equinox, so you can see that the daylight is decreasing almost down to half, and getting better all the time. It's good on solar. In the sky, 14th, this weekend is last quarter moon. The zodiacal light is visible in the east before sunrise for the second half of the month. The 19th, a very thin, well, not very thin, a thin crescent moon near Venus and Regulus. It's quite attractive. 20th of September, Titan's shadow transits Saturn's disk. As far as I'm concerned, this is probably your last chance to see it, because there's one more on the 6th of October, I think it is, and it's only a partial, so you're only going to get half the moon's shadow on the disk, and it's going to be up on the dark edge, the north edge, so it's going to be very difficult. Saturn is in opposition on the 21st, also new moon, and the following day is the autumnal equinox, 2:19 in the afternoon. Neptune in opposition on the 23rd. Double shadows transits starting at 1 a.m. on the morning of the 27th. Don't get up on the 27th and think, oh, I'll stay up late and watch it. 29th, first quarter moon. And in early October, the double shadow transit again at 3 in the morning on the 4th. And full moon on the 6th. You can see I didn't even put the Titan transit. T Corridor high in the west after sunset, still faint. I got accosted at the Ottawa meeting last night. Rick, you promised. You promised. I'll talk to management. Major planets. Mercury is huddled right in close with the sun. Mars is very, very low in the west after sunset. Saturn is, of course, and Neptune are both coming to opposition. So at their highest in the south, particularly Saturn, if you want to image Saturn, this is, when it's transiting the meridian, it's as high as it's going to get till next year's apparition. Uranus rises in the mid-evening and transits the beginning of morning twilight. Jupiter is high in the southeast in the morning sky. Kevin's already shown us that it's worth imaging. And Venus is moving back in towards conjunction, so it's getting lower in the east. Still bright. Small bodies. Ceres is in opposition on the 2nd of October, magnitude 7.6. First asteroid discovered. And a whole bunch, I've only got 5 here, because yesterday morning about another 10 showed up into my list. But so there's a number of them that we can watch. This one covers, I think, yeah, it's Cardinal and Borisburg. This one goes right across Kingston. So almost everybody up to Battersea, Sydenham, Centerville. Way up there off to the state.
Marks on the center one.
Yeah. Yep. Davidson Beach there. Darker Centerville's off the edge. Yeah, Battersea's pretty close. All the text down here is going to have disappeared, so it's hard to yeah. What's American? Well, I've been trying to restrict them to sort of brighter than 12th magnitude. I don't think we can manage anything 12th magnitude. So this one's actually an 8.9 magnitude star. I think 7.8 magnitude drop for 1.4 seconds. So that's actually probably one of the best ones to try watching. The ones that go. 11.7 magnitude star, just covers everybody except us northern crowd. It's a narrow one that I think is only good for Morrisburg. Oh, and Charlotte Lake. No. So we'll expect a report next month.
Yeah, that is.
This one is for the Athens crowd who are here. I checked, and actually there's a little pink house just off the corner of the main street in Athens. That's going to go through their yard.
That's where my brother lives.
In that little pink house. Any questions?
Yeah, what was all that? Would you say?
I'm sorry. Yeah.
Never
So
mind. I didn't pick up on that.
yeah. Basically, all these asteroids, minor planets that float around. Occasionally, they go in front of stars. And so this is the path. So this is the green line is the predicted center line of the path. The blue lines are the predicted edges of the path. And of course, we don't know exactly where the star is and where the asteroid is. So there's what's called a 1 sigma error estimate. And that's what the red lines are. So you can see, it used to be in the old days, you'd have a path like this, and the red lines, you know, the error estimates would be huge. Now they're down in off. Really, you know, we really know where things are.
So the blue lines are how big the asteroid is?
What's that?
The blue lines are how big the asteroid is?
No. I'm not entirely sure why, but they
Other
don't.
than projection on that.
Yeah, yeah. Yeah, that's the thing. I mean, you're not, you know, it's not overhead.
Right. For anybody who hasn't observed one of these things, the key point is that the shadow of the asteroid on the surface of the Earth is a shadowgram of the asteroid itself. And so you can, if you get a whole bunch of measurements across this path, what you can actually do is determine not only the size of the asteroid, but a projection of its state and shape. It's the only way short of going to an asteroid and visiting that you can actually get an accurate measurement of how big it is.
Yeah, so what you would do, for instance, is you might set up observers every couple of 100 meters or every kilometer across the road like this. And then, so the people down here wouldn't see anything. The people here would see just a very brief disappearance because it just, you know, the edge of the asteroid just catches the star. And then these people, you know, the opposite way. And by lining these all up, what they do is they draw chords. So for each observer, you have a line that it's green and then it disappears for a little bit because that's when the star disappeared. And what you'll find is you draw all these chords and you end up with a nice potato shape for the asteroid. At the orientation it happens to have at the moment.
And you have to have an accurate timing.
Yeah, they have very accurate timing and position, because of course if you're a little higher or lower or further back or whatever, things change. And what I have down here, I usually have the date and the time. 5 UT, then the name of the asteroid, the magnitude of the asteroid. The asteroids are usually very faint, and so they're completely invisible in the telescope. So all you do is you watch the star, and then the star winks out for a half a second or a second, or several seconds. And this is the name of the star in a UCAC4 catalog of stars. Its magnitude is 10.3. So because this is a 19th magnitude asteroid, when it gets in front of a 10th magnitude star, combined magnitude drops by 9 magnitudes. So the star disappears instantly. And if you happen to be right on the center line underneath the shadow, it can disappear for 36 seconds. Yeah.
How do you know the timing?
Well, what I've done here is I sort of take a midpoint. If you use the software, you can just click on it on your location and it'll give you the time to the nearest minute or so. So I sort of pick a midpoint, that's the time I put down here. So you should, if you were going to observe this, you would start watching 5 minutes before and go till 5 minutes after, or until it's already happened, if you actually catch it. I don't know if anybody here's seen one yet. I've seen a couple, but we've been trying this for a year or two now, and nobody's seen one yet.
What kind of software? Apple software?
This it's on the internet. It's called a Cult Watcher, and basically it runs on your computer and it goes out to external databases, and you specify that you need you want such and such a magnitude. Stars must be brighter than a certain magnitude. They can't be too low to the horizon. Has to be a dark sky. Has to be within 100 kilometers of your location. Stuff like that, and then it will go out and it will find all the stars, all the occultations that satisfy those conditions. Gives you a list on your computer. You just double click on it, and it comes up with these maps. Yep.
So they're running the cameras, big video?
That's your, if you wanted to try and time it,
Yeah.
or even just have a record of it, yeah, you would use
You have a time inserter on that?
I do not, because I'm not that keen on it. I'm mostly interested in just seeing it happen, because even just to watch it visually, to watch a star just disappear for
I
a
know
couple
they
of seconds.
changed the way, I always change the way they've done it.
Yeah, I mean, I've tried timing one with a planetary camera, and I just try and get it up to 30 or 40 frames per second, and then I make sure I check the time. I do an internet time check on the computer so that I know it's accurate, and then like 5 minutes later I get the video, and you can figure out at what time each frame was taken. So you can figure out exactly when it appeared and disappeared to within, a 30th of a second.
Is a planetary camera sensitive enough to get a star at 30 frames per second?
If your telescope's big enough and the star's bright, that's the limitation. That's why
Well, let me put it another way. For the things that you're presenting to us, a planetary camera and our telescopes would work.
You'd have to experiment. I don't know. I'm mainly putting them up here for interest's sake.
No,
Just
no pressure.
No, I know. No, I'm just saying though that
I'm just wondering how close to accessible it is.
Visually, you could do this easily.
Right.
So,
Rick?
yeah.
I've got a setup for this, and I use a CCD camera that is designed for video surveillance. So it's a commercial CCD camera, not an astronomical CCD. And I have time inserters that use the GPS time signal to generate a printed timestamp in individual frame. So I can time the events within a few milliseconds. And with a 10-inch telescope, I can observe several stars down to about 8th magnitude. It's been a while since I did one, but ballpark it's about 8th magnitude of 10. So, no. if you get keen on this,
I didn't think so.
There's technology out there using very sensitive cameras and very accurate timing.
But visually, I think you could do any of these with an 8-inch, 10-inch telescope. It'd just be nice if we got one. Then I'll stop pestering.
Well, that one that you showed going right near Mark, I thought, wow, try it out. I mean,
I I think one of them was an 8.9 magnitude star, your 12.5 inch. You know,
Like I'm using like a planetary camera, for example. It's a giant camera.
Yeah.
And I mean, to get a good saturated star, it's a 3-second exposure.
Yeah.
So, I mean, that doesn't work.
That's the whole ballgame.
well, I mean,
Exposure is longer than the duration of the occultation.
yes, yeah. I mean, but you're saturating your stars, you said.
Well, I mean, I'm getting them so that I get a good
Yeah.
PSF.
Yeah. So, you know, I mean, 30 milliseconds is 100 times faster. So, you know,
All right, I get you.
you might get enough signal to be able to detect whether it's
Experiment.
Yeah.
And
Yeah, and all you have to do is just take a field like get an AAVSO chart for a variable star or something. So you've got some reasonably accurate measurements of the brightness of some stars, and then just pick a field.
Yeah.
And see what exposure you need to do to get what magnitude.
I need a new observatory.
Yeah.
How did we go from this to that?
That's
Our
where it all,
cases is what you need.
that's where it all ends up now,
Paper
because we need a bigger telescope. Plane wave has a nice meter scope.
Plane waves belong in Chile.
Yes, Lord.
Are you gonna be posting this somewhere?
I think all of these ones were included in the what's up in the sky on the website.
Find it on the website and talk.
Kevin?
Oh, you know,
Nope.
there's, oh, no, I don't, I want.
Yes, I
earlier
did the
stuff.
last time.
Earlier stuff. I will check.
Anyway,
Cause I missed some, a couple things I wanted to know.
yeah. I think this is really the kind of stuff that you're better to run the software yourself. Because you want accurate maps. Oh, all the earlier stuff is on the Kingston RASC website.
Oh.
And in Reddit.
And then Google Calendar.
And in the Google Calendar. I guess we're done. I'll shut up for a moment.
You included accurate locations on the mainland and maybe what's up.
Good.
Could I mention something,
Yeah, go ahead,
Malcolm?
please.
Just if anybody is going to Fallen Stars and they haven't registered, I have registration forms here now. So just especially if you need to be loaded in for pizza dinner on Saturday night.
Did my email count?
Not really.
No.
You didn't say whether you wanted pizza or if you're staying over.
True.
Hard
I'll fix that.
You can fill in a,
still pay for the weekend.
you can
$95.
pay for the whole weekend just in case, Malcolm.
So if I could add on to that, it's unlikely that I will be at Fallen Stars, and in any case, I won't be bringing the vendor there. So want it, and somebody can come and get it and haul it there. Welcome to.
Start with the first one.
I vote.
This one. I'm hoping it opens on this window. Oh.
Oh.
So this is the Markarian chain. So following.
Sorry, I
Okay.
tried to make it full screen, but it went on the other screen.
So I know some of you attended Malcolm's astrophotography course, and one of the chapters of that course was on mosaics. So I decided to try a mosaic of the Markarian chain. So this is a very simple 2-panel mosaic. Just used Stellarium to plan it out. You get the RA and deck axis for each of the 2 panels, and then join it together.
Yeah, right up.
Much harder than doing ASIA or
Exposures.
that was about 60 exposures for each panel.
think each was about 180 seconds.
Is that a color?
Yeah, it's on a one-shot color, the ASI 2600 MC camera. Okay, yeah. So this is M81. This is just always wanted to try to take a photo of it. So this is about the same, about 50 frames of 180 seconds each. You can also see a few little other galaxies in the background. There.
Just companions to that?
I don't think they're companions, but I think they're just galaxies in the background. So it was after this one, my mount broke. One of those heavy wind stars we had. It pulled my cable out of the USB port and pulled the connector right out of the mount. So I switched over the next picture over to wide field. So this is lunar. So you can actually see the lunar X.
Yep.
Right here. So this is in July. So I actually had another telescope that I hadn't been using, so I prepared it using an old mount that I had. It was an old Vixen to prep it for Starfest. So go to the next picture. This is the picture I started taking at Starfest. This is the Dark Shark Nebula. I've always enjoyed seeing other people's pictures, so I thought I'd try it from Starfest. So I did the one night at Starfest, which was Thursday, was the only clear night that I was there, and I had to do another couple nights to get some more frames. So these are all at 5 minutes. I think it was about 140 frames over 3 nights. I think this is a galaxy here. Yeah. I don't know what these blue ones are. Yeah.
That's a great picture.
And that was it. So what's that? Scope and mount. Oh, it's for that. My old one, the one that was broken that just got fixed last week, is an Ioptron CEM 70, and the Vixen is a BXD2. Yeah, it should. And the Dark Shark Nebula was taken with a 75 millimeter scope.
Arcade. Yes. How should we proceed? Start showing. Number one.
Zoom can't hear you. Okay.
Zoom can't hear me?
Zoom can't hear
I think you were doing Zoom.
No, we're recording. Yeah.
Okay.
Oh.
So Kevin got me onto this. That? Kevin's fault. Yeah, it's Kevin's fault. So. Thank you, Shadow. And that was the first picture. Like I thought, holy smokes, I can see it. It's real.
This is easy.
Yeah, I know. This is like after about 2 hours of swearing and the equipment to finally get it all going. But anyway, so it just progressed. So.
So these are sequence of that event.
There are 2 events. So go to the next one, and it's a little further on. And then I was upset with the focus, so I went off to something else and focused and came back and tried again a little bit later on. Okay, and then one more. And then I tried binning to see whether that made a difference.
And all of a sudden you got smaller.
Well, yeah, it looks great, but it's smaller. And I think technically it would look lousy if you blow it up. And then what number are we at here? Okay, so this is the next. That was the first one. The first one was the date of the talk was
I can't tell from the screen.
This is the second one. So it was July 19th, 18th, 19th. And then the next one was 2 weeks later. The last one was done with my SCT, the 9.25 HD.
This says August 3rd.
Yes, and then again, August 3rd, there was another one. So, and so this one I did with my refractor. I thought I'd try it.
What did you prefer?
The Schmidt-Casper did a better job, but I think it's because of the native focal length. This, I had to put a Barlow, so it's a 5-inch scope with a 2.5 times Barlow. So it makes it into a 2.5 meter scope, but it's like f20. Whereas the HD is f10. So anyway, you can see, depth and then the shadow. It's just moved through, but the seeing wasn't anywhere near as good. And then this is the last one. Yes, this is the last. This was 2 nights ago. Can you see it? Can you see it?
Yes.
That's Ria's shadow. Go ahead.
Is this
Not there. Not there. This is the only one that showed up. I did a whole series. I knew where it was going across. Anyway, Ria's shadow. I tried it last night with Dion, and I couldn't see a thing. And this night, the night was awful. It was like foggy, and eventually Saturn disappeared. Yeah. And then last night it was a better night, but Dion is even smaller than Ria, so I didn't see it. Anyway,
awesome? What camera are you using?
ZWO676, one-shot color. So I think it's the same one Tim has. Do you have one too?
585.
Todd? You have a 585?
676 is the old thing.
Oh, okay. So you have the same camera, but you're using it.
Yeah.
Okay, that's it.
Yay, go planetary.
Uh-oh, out of camera 2021.
All right. Well, I thought I would show some of these here. So it's, yeah, we can show you. And,
Jack.
sorry, I'm trying to just figure out what to say. I was in Chile for 2 weeks, and this is a photo of the Gegenschein, which is the reflection from the anti-solar point on the solar plane. I'm almost right. I know I'm almost right. It's
So like that's backscattered from the dust in the plane of our solar
basically
system?
this, yes. It's a bright spot of that. It's like, it's the same illumination as a diode light, just from the anti-solar.
And I took another image of the same effect using panorama method. So this is, I think it's a 3-panel vertical panorama, which, I mean, perspective is weird because this is actually, you can see, so yes, so this is the Gegenschein. This is Andromeda. So one of the things I did while I was down there was I created my mount. And this is my scope over here, so the edge 11 and the and this is that setup in Chile close up. This is the new telescope that I added to the setup where this is a Astrotech 65 millimeter refractor. It's a 420 millimeter focal length telescope, wide field, but it replaced a broken on 135 lens, so it's wider than that, not as obviously wide or narrow a focal length or edge.
Doctor, why does all the telescopes have little skirts around?
Oh, just mine. I don't think anyone else's has.
Oh, is that just yours?
Yeah. So inside the skirt is our PC and the hand paddle for the mount and a bunch of stuff that we didn't want to get dusty. That's it. That's lots of other. If I go back one, most of the piers in here are steel posts. Here, this one here. We had the option of going with a steel post, and we already had the tripod, so we just shipped it all together. That's 3 amigos under the magellanic clouds. This is at I'd say 7. I think it's probably closer to 8 o'clock. Basically, just after darkness sets in, you can see the light still. Milky Way at the zenith, August. And this is a part panorama with the sky and the foreground shot at different shoots. The alignment is correct. The north to south. I mean, the Milky Way on the right is due north, and it ends due south. Which is where it is this time of year. Nice. Sorry, the Tropic of Capricorn sign in the foreground, and actually, it's been kind of destroyed since my first time visiting. All of these these are stickers all over, and tourists have this thing now. And I mean, where do you get stickers in the first place? I don't know. I think the tour guides are encouraging people to do this, but you know, what can you say? I have a photo of that before there were stickers on it. It's a lot more attractive. Morning planetary alignment with Venus and Jupiter. Moon and Mercury was behind the mountain. Fortunately, it's 20,000 feet away now. I was hoping to get Mercury, but it didn't. More Magellanic clouds from out in the desert. This was out of word. Okay, well, this is what the setup looked like in 2019. We set up the first time, basically just the one telescope. And this is the view of the building open. And I took a star trail, and just all I did was I stacked an hour or so time lapse into a single frame. That's the south pole. See that? And there's zodiacal light after sunset. It's pretty dramatic.
You see that with naked eye?
Absolutely. Oh, yeah.
What time? Day or night?
You know, 8 o'clock, 7:30. 7:30 and 8. It starts to. In fact, I have a time lapse I'm going to show you. How it lasts, I think. Speaking of time lapses. One.
After the bar.
This,
Up
up on the controls for the video. To the left.
Oh, there. Okay, let's see if this works. No. No, I don't want this. First. Sorry, I'm using two different screens. Sorry. Just as well. Motorcycles.
Is that part of your soundtrack?
What?
Is that part of your soundtrack?
Yeah. So what I have to do is I have to open it and then drag it over to the other screen. But when it opens in full screen mode. It doesn't give me anything to click on to drag it over to the other screen. So
Can you exit full screen?
it's actually not in full screen. I thought it was. It's just the new version of DLC. I don't understand the interface. Sorry. Okay, well, forget it. No sound. So. Open it and just see it right in there. That's just rising. Hey, I did it. Let's turn this one off. No. No. Yeah, we're at the end of the program. Check out our website at kingston.rasc.ca. We have a Facebook group. And this meeting will hopefully be on YouTube sometime in the future. If you're not a member of the Kingston Centre, you're invited to join us. Brian. I've got the old date from the last meeting. I didn't change the slide. I'm sorry. Next month's meeting is our speaker has not been determined yet, so we'll announce that soon. But it will be in October at 7 o'clock, and it will be at our regular meeting room on the second floor. And I guess there was one more thing. The oh no, Susan mentioned all the stars, so that's it. Thank you for attending, and we'll see you next time.